Hey everyone, so today we are talking about percent yield. It is once again just another extra step added to our stoichiometry problems. Well, what is percent yield? Percent yield is actual yield over theoretical yield. Well, what are those, okay? Well, theoretical yield is what we've been finding this whole time. Any stoichiometry problem we do, whenever we get the answer at the end and we circle it, it is our theoretical yield. It is if conditions were perfect and every molecule bumped into each other and reacted, it would produce, say, like 20 grams of CO2. But in real life, things don't work out well. The temperature isn't quite right. Those molecules don't ever actually all hit one another. And we actually get something far less than our theoretical yield. Sometimes we get more if there's some impurities in there. So theoretical yield is what we get from our stoichiometry problems. So whenever you do a stoichiometry problem and you solve it and you get an answer at the end, that is our theoretical yield. Actual yield is what we get in real life or in lab, okay? So we might do a reaction where I say methane is reacting with oxygen and we have a certain amount of these and it should produce 20 grams of CO2 based on my stoichiometry problem. But then we go into lab and we actually conduct the experiment and we might only get 15 grams of CO2. So actual comes from real life, theoretical comes from our stoichiometry problems. I will always give you actual yield, okay? I will always give you how much we produced in lab or in real life, but theoretical yield you will have to find, as usual, from our stoichiometry problem. So once again, like I said before, it's just stoichiometry with extra steps. So let's go ahead and let's put this into practice and see what this percent yield is all about. So here is our first problem. It says 4.20 grams of calcium hydroxide reacts with excess HCl. So this isn't a limiting reactant problem. It already told us we have too much HCl and our limiting reactant is CaOH2. So that's good. We know we don't have to do a limiting reactant problem. This produces 1.62 grams of water. Okay, calculate the percent yield. So the first thing I want you to do when you have problems like this is I want you to find the actual yield first. So whenever it says calculate percent yield, I will always give you the actual yield in the problem. Let's go ahead and identify that first. So what we're looking is for something where it says produces, yields, creates, in lab we came up with, okay? So we're looking at this and it says that this produces 1.62 grams of water. That is our actual yield. It is the mass of one of the products that it gave us, right? So in lab, we came up with 1.62 grams of water. So this is going to be our actual yield, this 1.62 grams. So we're going to set that off to the side, and we're going to use that later when we do actual yield over theoretical yield. But now I need to find that theoretical yield, right? But the only thing they gave me was 4.2 grams of calcium hydroxide, right? Well, we got to figure out that if conditions were perfect, how much H2O would that actually produce? So we got to use our handy dandy friend stoichiometry. So they gave us a reactant, that 4.20 grams of calcium hydroxide. Let's go ahead and see how much in perfect conditions that will produce of water. We know we are changing it to water because they gave us the actual of water, right? So we're going to need the theoretical of water. It wouldn't help us to get the theoretical of CaCl2 because we're not comparing those. We're comparing the actual of water with the theoretical water. So let's go ahead and let's do this stoichiometry-wise. Let's make sure this equation is balanced. It is. I did that for you. You're welcome. So let's go ahead and go to step 2, which is change grams to moles. And I believe calcium is 40, and then OH2 is 17 plus 17, which is 34. So this molar mass of this guy is 74 grams per mole. So we got grams of CaOH2. We divide by the molar mass to get to moles. So I'll take 4.2 divided by 74, and I will get something around 0.057 moles of CaOH2. Cool. Again, step 3 is mole ratio. We gotta do mole ratio time. And we know that we are changing this to water, right? We want to go from moles of calcium hydroxide to moles of water, and that's because we already have that actual of water. Now we need a theoretical. Calcium hydroxide on top, calcium hydroxide on bottom. I know that looks confusing. Let's go ahead and let's switch that because I don't like that, because that might be confusing because it might look like calcium hydroxides on bottom. It's not. Okay, calcium hydroxide on bottom. Once again, on top is going to be our H2O, right? We already have the actual. We need the theoretical now. Calcium hydroxide has a 1 in front of it. Water has a 2. So 0.057 times 2 is 0.114. So now I have 0.114 moles of H2O. Moles are nice, but can't help me now. I got to get to grams, right? So let's multiply by the molar mass of water, which we should have in our brains as 18. So 0.114 times 18 gives us a theoretical 2.05 grams of H2O. And again, that is our theoretical because that's what we got from stoichiometry. If conditions were perfect, that's how much water we would produce from this reaction. But reactions or situations aren't always perfect. All right, so let's go ahead and now let's find out our percent yield. Remember, our percent yield is actual over theoretical. So our actual, we identified at the beginning as 1.62 grams. Our theoretical, we found from stoichiometry, which was 2.05 grams. And then, remember, we must times by 100%. This is percent yield, it's not fraction yield. Okay, so we times that by 100%. And we got 79% yielded or recovered. So what this is saying is that through this whole reaction, we got 79% of what we should have. If things were perfect, we would have got 2.05 grams of H2O, but actually we got 1.62 grams of H2O, so only 79%. Okay, this isn't bad. All right, it's really hard to get high yields out of some reactions. Some companies have done a really good job of getting their yields pretty high. You can have a percent yield over 100. Sometimes, we might get some impurities in there. We might get some liquids that aren't water in our reaction that might increase our mass and give us a percent yield higher than 100%, which means we just have some impurities in there. Okay, so let's go ahead, let's do another couple reactions to make sure that we have this down. Next example for us, it says determine the percent yield. Okay, we know what we're doing right off the bat, percent yield, for a reaction between 5.29 grams of NaBr and excess chlorine gas if 3.95 grams of bromine is actually formed. So again, percent yield, the thing I like to do right off the bat is figure out my actual. My actual is a product. Okay, and what it says is that 3.95 grams of bromine is actually formed. Okay, I pretty much just threw it right in your face. Actually formed, actual yield. So this guy right here, this 3.95 is our actual, and it was of bromine. It's always going to be a product. So there we go. So that means we got to find theoretical of bromine now through stoichiometry. So let's see what they gave us to work with. Well, it looks like the only thing they gave us is 5.29 grams of NaBr. It says chlorine gas is in excess. Good, so we don't have to do a limiting reactant problem here. They already told us pretty much that the limiting reactant was NaBr. So we got 5.29 grams of NaBr. We got to get to grams of bromine, right? We got to get to that theoretical. So let's go ahead and let's do this. We got to get to moles first, right? Oh, let's make sure it's balanced. 2, 1, 2, 1. Yep, that looks good. Okay, so let's go ahead and now change our grams to moles. Moles is the universal language of chemistry, right? So the molar mass of sodium bromide is 23 plus, let's just go with 80. 103 for simplicity's sake. So the molar mass of NaBr is 103. 23 plus 80 is 103, right? And that'll give us moles. of NaBr. Let me go ahead and plug this into the old calculator. It is 0.05, we'll go with that, moles of NaBr, right? But we don't want moles of NaBr, we want moles of bromine because that's what we're trying to get to, right? They gave us the actual of bromine. We need the theoretical of bromine. So NaBr is on top. Remember, we want NaBr on bottom so they cancel out. And then we want what we want on top, right? Our bromine, that's what we're trying to get to. And then whatever the coefficients are what go in front of those. So bromine's got a 1 in front of it, and NaBr has a 2 in front of it. So we're getting even smaller here. So NaBr is going to cancel out. I'm going to take 0.05 times 1 divided by 2, or just times by 1/2, right? And now I have, we're going to go down here, 0.025 moles, no longer of NaBr, but of bromine, or Br2, that diatomic molecule. And again, they gave us our actual in grams, so we better get our theoretical in grams as well, which bromine by itself, just Br, is 79.9 or 80. But we got 2 of them now, so it's going to be 160 for a molar mass. I can't do this in my head. I'm going to say 4 grams. That's what I'm going to say. That's what I'm going to guess. Your chemistry teacher is smart. It is 4 grams of Br2. Okay, so once again, that is our theoretical. If everything was perfect, we would have got 4 grams of bromine. Hey, we're looking pretty good. We got pretty dang close to that theoretical. Let's go ahead and find the percent yield now. I'm going to do that over here. So remember, percent yield is actual over theoretical. Well, our actual was, oops, let's make that a little bit darker so you can see it, 3.95 grams. And our theoretical was 4 grams. We're going to take 3.95 divided by 4. Remember to times it by 100 because we're dealing with a percent yield here, right? And I can't do this math in my head, unfortunately. Times it by 100 to get a percent, and you should get 98.75%. That is a pretty good percent yield. We almost got 100%. I don't know if you'll see anything like that in the real world of chemistry. That's pretty hard to come by. So once again, that is percent yield. Let's do one more example, but this time let's have it where we also have to do a limiting reactant problem. So we're going to have to navigate the wording of this problem a little bit more. So let's go ahead and try that one out. All right, everybody, the most difficult percent yield type of question you will see. In a reaction between 1.25 grams of KCl and 2 grams of AgNO3, a mass of 1.52 grams of AgCl is recovered. What is the percent yield? Here we go, guys. Percent yield problem, but here we got 3 masses now. They gave us a mass of KCl and a mass of AgNO3. Those are what are going to react to form our theoretical yield, right? It's going to produce something. In this case, it's going to be AgCl and KNO3. Well, which one are we focusing on? We are focusing on AgCl. Why? Because it says a mass of 1.52 AgL is recovered, right? That is going to be our actual yield, this 1.52 grams of AgCl. It was the product. It's what was recovered, produced, yielded, something in there where it says that we created something. In this case, it's AgCl. Well, now we got to figure out the theoretical of that AgCl. The problem is that I didn't just make it simple and tell you that one of our reactants were in excess. I gave you both of them. So we got to figure out which one is in excess all on our own. And that means doing 2 stoichiometry problems. So let's get to it. So we got to balance this. It's balanced. Okay, it's all 1-to-1 ratio. Everything has a +1 or -1 charge. Let's go ahead and start with, we have 1.25 grams of KCl, and let's go ahead and let's put 2.00 grams of AgNO3. We got to get both of those to moles since moles is the universal language, right? So let's divide by the molar mass. Potassium is 39.1 essentially, and chlorine is 35.5. So we're going to have 74.6 grams per mole for our molar mass of KCl. Silver, I believe, is 108. Nitrogen, I always forget that one for some reason, is 14. And oxygen is 16. We got to do 3 of them because it's NO3. And we should get a molar mass around 7. So we should be able to get the moles for both of these guys. 1.25 divided by 74.6 is 0.017 moles of KCl. I like to write out what product I'm dealing with just to help me in the mole ratio step. And 2.00 divided by 170, that's going to give me 0.012 moles of AgNO3. So step 2 is now done. Step 3, mole ratio time. Remember, multiplication dot fraction bar. And what are we trying to get to? What compound? Well, remember we have an actual yield of AgCl. We're going to need a theoretical yield of AgCl. So what we have on bottom, we have KCl there. We have AgNO3 on bottom. And what we want on top, which I just said, was AgCl. But does it really matter? No, because they're all 1-to-1 ratio, right? So this is some nice simple maths. We're just going to end up with the same thing. We're going to have 0.017 moles of AgCl now and 0.012 moles of AgCl. And now we got to ask ourselves, which one's the limiting reactant, right? Which one's going to run out first? It's going to be the one that's smaller, right? Hot dogs and buns, right? You always run out of hot dogs first. So our limiting reactant is the smaller one, which is this one. So it was our silver nitrate. Our silver nite is what kept us from creating more of that silver chloride. So again, we don't care about this guy. Now we're just focused on that bottom number there, that 0.012 moles of AgCl. So let's go ahead and erase this, and let's go ahead and convert that to grams now. Well, I gotta multiply it by the molar mass of AgCl. Again, Ag is 108, chlorine is 35.5, for a total molar mass of 143.5 grams per mole. So we multiply those together, and we'll get something like 1.72 grams of AgCl. And remember, that is our theoretical. In perfect conditions, that's what we get. So now we have theoretical. They always give you actual. It is time for some percent yield action. We got 1.52 grams of AgCl over our theoretical of 1.72 grams of AgCl. We times them by 100% because this is percent yield, not fraction yield. So 1.52 divided by 1.72 times 100, you'll get 88.4% recovered. Not bad. Okay. Again, you could have a percent yield over 100%. Most times it's just under 100%. We usually don't get to that actual number, but sometimes we do get impurities that push it over 100. So that is percent yield. Okay, make sure you're putting actual over theoretical. I always give you actual. Theoretical comes from stoichiometry. If you have any questions, please let me know, and have yourselves a great day.